So we are continuing our discussion on solving linear systems, and today I will just briefly review what did we do for Gaussian elimination, and then we will actually go and look at how do I come up with a system of linear equations. So we will actually have two examples of situations where I actually derive in a situation of engineering interest, I derive a system of linear equations, and then we will solve that system. So that should motivate you a little more, even a little more, to learn about solving linear systems. And the reason I did it this way is that first let's learn about something how to solve simple systems, so we have some idea, okay, I can solve this, and by now you should have that idea. And now we will actually get into designing linear systems. So just a quick review. So if I do have a system, here is an example of a 3x3 system, like a general system. So if I want to solve it, there's one most famous method. It's called Gaussian elimination. And the way it proceeds is that it basically, so here I have these three coefficients that are on the lower triangular part of the matrix, and basically I'm trying to get rid of them. Get rid of them means that I'm gonna do linear, I will replace certain rows by linear combination of the others and with the objective to set these three values to 0. And then once I do that, I will have an upper triangular system. Upper triangular system we can solve by what we call back substitution. So for instance, if I had these two 0, I would have 0, 0, A3, 3, and B3, and then of course A3, 3 times X3 is equal to B3, so I can immediately solve for X3. And once I have X3, I'm going to plug it into the equations above and first solve for X2 and then for X1. So that is called back substitution. So formally, and if you were to program this, basically you can come up with a systematic way of what do I multiply my first row with. So if my first pivot position is this one, I will multiply this first row by A21 over A11 and basically subtract the second row, and once I do that, I will essentially arrive at the 0 at the desired position. And then I proceed a very similar procedure. I proceed and I will get zeros in the first column. And then I have these new, I'm now calling them tilde, A22, A23, A32, and A33 tilde, so slightly modified coefficients. And I basically now multiply the second row with an appropriate coefficient and subtract the third one, and then I will get a 0 here. Okay? So this is something that actually can be programmed, and we will get to the programming of this procedure next week. Okay? There are some pitfalls that I have to be aware of. First one is that I could have a 0 in my so-called pivoting position. So if I have a 0 here, then I cannot use this row to get rid of anything below it, right? So basically what I have to do is I have to switch rows. So I'm just going to flip these two and proceed with my calculation as before. Typically, if you were to program this, you would basically find the largest coefficient in the column below and switch those two rows. That does not really change the solution of the system at all. Okay? Sometimes you might actually want to switch columns, but the moment you're switching columns, you have to be aware that you're switching what is X2. Let's say that I'm switching columns 2 and 3, then what is X2 becomes X3, and what was X3 becomes X2. And that might or might not be important in my application, but I'm actually renaming my variables if I start switching columns. There's a lot of operations, and we will actually get to those examples a little later. There's a whole lot of subtraction and division and addition in Gaussian elimination. So in the 3x3 system, it's not all that important and it will not come up as a huge issue. But if you have very large systems and in any proper engineering applications of interest, it could be up to 1 million, you will actually have a whole lot of additions, so the round of error will pile up. Okay? And that can actually affect the solution. So technically, there are other methods to use other than Gaussian elimination when your number of equations is larger than a few hundred. And we will get to those as well. And then there are so-called ill-conditioned systems. I think not in this homework, but in the next homework we will give you some examples. There are certain bad matrices A, or coefficients A, where a very small change in the coefficient can produce a very large change in the solution. And those are so-called ill-conditioned systems. It's not really a round-off error issue, it's just that the system is badly conditioned, so it's not going to give stable solution. If these are sort of solutions to physical problems, then I would expect that whatever it is that I'm solving for in my system, if let's say that there's something to do with modeling temperature in this room, and there are certain boundary conditions, as in what is the temperature outside, I would hope that the very small change in the temperature outside will not disturb whatever the temperature here greatly. Right? And if it does, I have a so-called unstable system. So air flowing over here is not going to produce an unstable system necessarily, but if I have turbulent flows in very large pipes, those are very unstable. And there are actually examples where you will, small perturbation of conditions in temperature and so forth can actually produce a large error in solution. Okay, so now we will go back to examples, and this time we will actually come up with or design our linear systems. So this is basically linear systems that solve problems of engineering interest. So here's a bunch of reactors. So this is a chemical engineering problem. So let's say that I have a reactor 1, a reactor 2, and the reactor 3. There are certain reactions that happen in all of them, and I'm bringing the species to the reactors. I'm not naming the species at this point, but basically there's a flux, steady flux in, which is 100 meters cubed per second. So that is coming into the reactor 1. Call this one 2 and this one 3. So this is a system of reactors. And then I have this reactor 1 is actually outputting stuff to number 3. And that flux, I don't know what it is, but I'm going to call it Q13. And also to number 2. Again, I don't know this one either. I'm going to call it Q12. Now 2 is also communicating with both of these. And there is a line going from 2 to 3. And that one has flux Q 2, 3. And there's also output back to number 1, and this is Q2, 1. And I'm bringing a flux in the order of 20 meter cubes per second into 3. And then I have output here that I'm calling Q33. So there is a basic mass conservation law. So if I'm designing a system like this, I want to decide what's called a steady state flow through the system. That means that what is the size of these fluxes does not really change in time. I have at every time point I'm going to have the same Q that I see here. So design steady state flow. Through the system. And that basically means that whatever comes into each reactor has to be equal to what comes out. Okay, I have to have a mass balance. There's no accumulation anywhere. So what comes in equals what comes out. So with that in mind, if I'm just looking at 1, 2, 3 together as a system, what is coming into the system? What is the amount per second? What is the flux that comes in? Only 100? That's what's coming into 1. But in the entire system, 1, 2, and 3 together. 120, right? So that's what's coming in. What's coming out of the entire system. Q33 is my communication to the outside, right? The rest is just recirculation within the system. So if I'm just looking at the system as a whole, then basically what comes in, right? So entire system, what comes in is equal to 100 plus 20, which is 120 meter cube per second. Out is essentially Q33. So Q33 is not really a variable. I already know Q33 equals to 120 meter cubed per second. So that's this conservation principle applied to the entire system. Now we will actually get the equations for all of the other fluxes in between. I'm going to apply the same principle for each reactor separately. Okay? Because at steady state, it actually has to be true for every part of the system. So whatever comes into 1 has to be equal to what comes out. So basically, now let's apply the same principle to all reactors. 1, 2, and 3. Okay. So I'm gonna switch to the page, but I hope you have notes so you can help me out. Okay. So what comes into 1 and what comes out?
You have 100 plus Q21.
And what comes out?
Q13 plus Q12.
Does everybody else agree if you have your notes? Okay. That's my actually first equation. My second equation will come from reactor number 2. Can I have another volunteer for reactor number 2? What comes in? Q12. Anything else? No. What comes out?
Q21, Q23.
Does everybody agree when you see your picture? And finally, the third one. What comes in? Q13 and Q23.
Oh yeah.
And plus 20, yes. And what comes out is Q33, which is 120, so we can actually write that down. Everybody clear? Okay. How many unknowns do I have? So there's Q21, Q13, Q12. This is the same as Q12 already, Q21, Q23. And that is 4 altogether. So I have 4 unknowns. And 3 equations. So that will there be a unique solution to this system? No, I don't have at best a class of solutions. So they will all conform to certain final equations that I have, and that is okay. For a system like this, I mean, you don't want to have a system where like you have precisely one solution and no other, and then there's no way for you to hit that solution when you're designing the system, right? You would like to have a class of solution to the problem. So basically, there will be no unique solution. So let's set this up into a form that we can actually solve. So I'm gonna just reorganize them a little better. Q13 minus Q12 is equal to minus 100. So this is my equation number 1. And then Q12 minus Q21, that's my first one. So I'm just trying to line them up. So it's going to be minus Q21 plus Q12 minus Q23 is equal to 0. And then I'm going to have the last one. Again, I'm trying to line them up. Q13, Q23 is equal to 100. Okay. So basically, this is what my x1 was. We can rename it x1 if you want to, x2, x3, x4, right? So those are my 4 unknowns. So the system here that corresponds to this is 1, minus 1, minus 1, 0, minus 100, minus 1, 0, 1, minus 1, 0. 1, 0, 0, 100. So what we are used to doing in Gaussian elimination, even though I will not arrive at the unique solution, I can just proceed as I did. So basically, I can, in order to get a 0 here, I can just sum up first 2. So I'm gonna have control So basically what I'm gonna come up with, can somebody give me what I'm gonna come up with? So first one will be, what is my first row? Anybody?
1, -1, -1, 0, -100.
Okay. And when I sum up the first two rows, what will I get?
0, -1, 0, -1, and -100.
Okay. And the first one remains the same, right? Is it 1, 0, 1? What was it? 0, 1, 0, 1? And -100 as well, right? Positive? Okay. I diverged from my notes, so now I have to ask you. All right. So now I have my second pivot position will be this one. I'll just make it all positive. I can just do it here in place. So multiplied by -1. And now this is my position. So basically, look at what I can simply do here is replace by 3 minus 2. Now what? What does this mean?
It's useless.
The last equation is useless. I still have a system to solve. Okay. So this last one is not nothing. It's actually just cannot use to constrain the solution. So basically my system is this one. Let me just write down what these were correspond. This was Q21, right? This was Q13. This is Q12, correct? And this is Q23. Is that how? So basically I can really solve for Q13 and Q21 in terms of the others. And the other two, Q12 and Q23, are variables. So basically I can use my back substitution just fine on these two, right? So I can solve for Q21 and Q13, and in terms of Q12 and Q23. So essentially from this is now a back substitution for my equation 2, Q13 is equal to 100 minus Q23. And from my equation 1, Q21 minus Q13 minus Q12 is equal to minus 100, and I can replace this one with this. So my Q21 is equal to, on the other side, Q13, which is 100 minus Q23 plus Q12 minus 100. So that is Q12 minus Q23. And Q12, Q23 can be any positive flux. And for any positive flux, I'm going to get a solution to this. Any two pair of positive fluxes, Q1, Q2, Q2, 3, I will get a solution. Why positive? Simple physical constraint. You cannot have minus. Well, minus 20 could involve the direction, but here we added direction ourselves, so our fluxes have a direction. Make sense? Now, when I have a system like this that is not fully determined, whether I'm expressing, in this case, Q21 and Q13 in terms of the other two, or I'm expressing Q12 and Q23 in terms of the first two, it doesn't really make a difference. Okay? It's just the way I ordered them in the system, so I ended up solving for the first two just simply in the way I ordered them. So that part, that much is up to me. Questions? All right. Let's go to another problem. Okay. So my next example will be a model of a heated rod. And will essentially involve a solution, numerical solution to a differential equation. How many of you have taken differential equations already? How many of you are doing it right now this semester? That doesn't add up to everybody. Okay. You have basic knowledge of differential equations. Again, we're not going to really solve for differential equation analytically here. We're just going to mention the one that is the rule. So this is heated rod model. So this is another application for a linear system, and actually a very, very common one. So assume that I have a heated rod and this rod is 10 meters long, so this is, I'm going to call it location x0 is equal to 0. This is location x, well, I'm going to label it immediately, x5 is equal to 10 meters. And I'm keeping this ends of this rod, both ends at temperature. On one end, T0 is going to be 40 degrees Celsius, and on the other end, T5 will be 200 Celsius degrees. Now this rod is not insulated. And there's some ambient temperature TA. TA is ambient air temperature. And I will assume it's 20 Celsius degrees. So essentially, I know that if I have heated rod like that, it's at the temperature higher than the ambient temperature. The moment I have a gradient in temperature, I'm going to have some heat losses to the rod. Okay? So it's going to cool. Now, we know those rules in general, transport will happen when you have gradient. If you have gradient in pressure or differences in pressure, you will have flow. If you have differences in temperature, you will have heat transport. If you have differences in mass concentration, you will have diffusion. So if there is a difference or gradient in some basic property, you will have transport occur. So in this case, it's heat transport. So the governing differential equation for temperature at every point of the rod is that the second derivative, dt dx squared, is going to exchange some heat And basically I will have a heat coefficient H, TA minus temperature itself is equal to 0. So this is my differential equation that governs. And this coefficient is actually telling me, it's a property, material property that tells me how does this exchange between the rod material and the ambient air happen. And I'm going to call H heat transfer coefficient. So there's a certain rate of transfer between the rod and the air. And it's given per length, so it's in this particular case 0.01 meter inverse, or 1 over meter. So I can also see that essentially the larger the difference between the temperature of the rod at a given point and the ambient, I'm going to have a larger transfer. So at this end where I have 200 degrees, I'm going to have more flux out, or basically more heat transported out of the rod than I will have on this end that is at 40 degrees Celsius, right? So that makes it a little even. I don't have a constant transfer, or my transfer is not constant along the rod, so this is why I need to actually solve a differential equation. I can't just go by hand. Now, how are we actually going to numerically solve this? And this is a common approach in all of the sort of discretization of differential equations. First thing, whenever I'm solving things numerically, I will not get a function solution. I will not get that t of x is some function of x. Okay? That's what analytical solution is for. What I will get is I will simply solve for values at certain discrete points. And how many discrete points depends on me and how do I want to what's called discretize this problem. So what I will do is I will say, okay, let's solve for 4 points in between, and I will equally space them. Yeah? So this is my location x1, this is my location x2, x3, x4. So discretize the problem. We will find temperatures, and I will refer to the temperatures as T1, T2, T3, T4 at 4 equally spaced locations. X1, X2, X3, X4. I don't need to look for T0 and T5, they're already given as boundary conditions. So my boundary conditions are T of X0, which is T0 is equal to 40 degrees, and T of X5, which is T5, it's equal to 200 degrees. So those are my boundary conditions. So this is essentially the problem I'm solving. No differential equation is complete without boundary conditions. So now I want to actually, essentially what I need to do is I need to set up equations for T1, T2, T3, T4. And what will enable me to do that is basically expressing, at every point I can express derivative at that point, derivative of temperature at that point, based on the surrounding values. Now you know already that if I had, let's say that I'm looking at this point T1. So at this point x1, or location x1, I know that I can approximate dt dx, or derivative of this function. So my temperature is a function of x. And I can approximate t of x2 minus t of x0 divided by x2 minus x0. Is everybody following what I'm doing? So this is an approximation of a derivative of a slope. I can actually, now you might have not seen that one, but I can actually then, for dt dx squared, okay, I can basically apply a very similar rule and just apply it to dt dx and then approximate it further. And I'm not going to do that directly here, but you could actually get the formula that dt dx squared is approximated as t of x2 minus 2t of x1 plus 2 of x0 divided by what I'm going to call delta x squared. And delta x squared is this spacing here. So this is a general, what's actually called a finite difference formula that expresses an approximation to a derivative based on the values of the nearby points. Okay. So a more general formula, I'm actually going to, so this is valid at tx1. Let me control 0. So a general formula for approximating derivatives is dt dx can be approximated as, minus t of x minus delta x divided by 2 delta x. So this is for first order. T of x plus delta x minus 2 t of x plus t of x minus delta x divided by delta x squared. So these are so-called finite, and actually they're kind of centered at a point, so we're actually calling them central finite difference. Oops. Apparently I don't know how to spell finite. Okay, so now let's go back to our differential equation. I know that that differential equation is valid at every point. That means that it's valid at location x1, it's valid at the location x2, it's valid at the location x3, and so forth. Okay? So if I apply the formula, so back to my differential equation, I know that dt dx squared, d squared t squared, plus h times ta minus t is equal to 0. Well, this is actually true at location x1. Right? So at location x1, when I apply that, then basically this can be approximated based on this as t of x plus delta x, x1 plus delta x, minus 2t of x1 plus 2t of x minus delta x, x1, divided by delta x squared, plus h times ta minus t of x1. is x1 plus delta x? In terms of my locations, how did I name that? It's x2. And t of x2 is what I call t2. Okay? So essentially, this is same as t2 minus 2. This is t1. This is, and x1 minus delta x is minus x0, right? So that is t0. Because this is x0 and this is x2. Now, what is delta x in this particular case? I have a drawing. I have 10 meters altogether. How many segments do I have in that picture? I don't have the picture here anymore, but how many segments were it? 5. So basically, my delta x is 10 meters divided by 5, which is 2 meters. So this delta x squared is 4 here. Plus my H is 0.01 times TA, ambient temperature was 20, minus T1 is equal to 0. Gonna multiply this by 4. So this is going to be T0 minus 2.04 T1 plus T2 is equal to minus 0.8. Everybody okay with this so far? So I got one equation that expresses something that is true about 3 of my temperatures T. In this particular case, I'm only looking for the 2 of those, right? T1 and T2. T0 is already given as a boundary condition. But so far, this is true. So I'm just going to rewrite this slightly differently. And there is a reason why I want to have a positive number here, so I'm just going to multiply it with a negative 1 and go to a next page. So I'm going to have minus T0 plus 2.04 T1 minus T2, and it's equal to minus 0.8. Or plus. If I applied this now to the next set, I would get the same equation. It's just going to be shifted by 1. So it's going to be equation in T1, T2, and T3, correct? And the next set, so let me just write them all down. So I'm going to have minus T1 plus 2.04 T2 minus T3 is also equal to 0.8. And I'm going to get the same thing if I apply it at the point x3. So I'm going to have minus 2 T2 plus 2.04 T3 minus T4 is equal to 0.8. And my final equation is going to be minus T3 plus 2.04 T4 minus T5 is equal to 0.8. And as much space as I wanted to leave to line all of these up correctly, I did not. Oh, and then I threw in a 0 just for kicks. This is a linear system of linear equations. What are the ones that we actually don't know? Mm-hmm. So those are the ones, we don't know 4 of them. And these are boundary conditions, right? So they can actually go to the right-hand side. So T1, T0, T5 are known. And this one was 40, and this one was 200. So minus 40, minus 200. So I'm not going to rewrite the system. I'm actually just going to rewrite it as a matrix form. So my system is 2.04 minus 1, 0, 0. And on the right-hand side, I'm going to have 0.8 plus 40, so it's 40.8. And then I'm going to have 0, minus 1, 2.04 minus 1, and 0.8. 0, 0, minus 1, 2.04. Did I shift anything? Yeah, I shifted things. You can essentially see which days I stay up till 2 a.m. by the amount of mistakes I make in class next day. So this is minus 1 here. And this last one is going to be 0, 0. So this is my T3 minus 1, 2.04. And this is going to be 200.8. So this is a linear system that we can solve. This is a special form linear system. It shows up a lot. It's called tri-diagonal system because I have only 3 diagonals. That have non-zero values, and I have 0 values everywhere else. And we can plug it into MATLAB and solve it, but I don't think we have time to do that now. But we will actually mention how we will also solve it by hand. The solutions are not that pretty to solve this by hand, so we will not proceed by hand. We will actually use MATLAB.